Okay, guys, so let's get started. Today we'll talk about how to produce electricity using solar energy. Okay, and as you've seen, a Stanford University group has predicted that by 2050, a little more than half your energy can come from solar energy. Okay, so we'll see how you can produce electricity using solar energy. You guys have seen solar panels, okay, out there, and we'll talk about how the solar panels work. The story is a little complicated. Well, it's a little involved, so you have to, if you want to understand it, you'll have to pay close attention. Yeah. All right, so electricity from solar energy. Okay. This is how much sunlight is falling on the surface of the earth. This is how much solar energy you're getting. You can run the world on that. Okay, so there's plenty of sunlight falling on earth just to run the planet on just solar energy. Okay. And here's a calculation. Okay, so what this says is total solar energy reaching Earth's surface, the surface of the earth, is 9 times 10 to the 16 watts. Okay, so if you go above the atmosphere, it's about twice that much. Okay, so people have talked about putting solar panels in orbit, and you could harness more. But of course, it costs money to launch stuff and all that. So this is relevant. Okay, so this is how much solar energy is falling on the surface of the earth. A gigawatt, as we've talked many times, is a Hoover Dam roughly. Okay, with that you can run 1 million homes. To run our planet currently, you need 18,000 Hoover Dams. Okay, this is with the mixture of fossil fuels and stuff like that. If you produced all electricity, you guys remember that you need less than that. But let's say even if you need that much to run the planet, what this is showing you is 18,000 gigawatts is 1 billion watts. 10 to the 9 plus 3 is 10 to the 12 plus 1 is 10 to the 13. There's that. And okay, cheap solar, assuming a 15% efficiency on the solar panels. Okay, so that's how much energy is falling on the earth, solar energy. You can only harness 15% of that. Okay, so 15% of that, and this is the power needed to run the planet. Okay, so if you do this calculation, what this is saying is all you need to harness is 0.1% of the solar energy falling on earth to run the planet just on solar energy. Okay. This is great. It's free. It has 0 carbon footprint. It's clean, and you won't run out of it for another 5 billion years. Okay, so it's got all good qualities. Okay, so that's where the future is. So what's preventing us from doing this? Right now, solar and wind are the cheapest sources of energy. No, I just said it's the cheapest source of.
We don't have big enough batteries.
Batteries is okay. So what do you do at nighttime? Because the problem with these renewable sources are they're intermittent. Okay, most of the wind energy at a given location you'll get it in 2 or 3 hours. But you need electricity 24 hours. Okay, so batteries are okay. So if we only had cheap batteries for nighttime use and all that kind of stuff. So here's the number that you can keep in mind. Okay. In a net zero scenario, what does that mean? A net zero scenario. What are they talking about? No carbon dioxide emission. And how do you get there? By using wind and solar. Okay. So you could run the world in wind and solar the world would need about 1,000 gigawatts of storage technology. 1,000 Hoover dams worth of batteries, whatever. Okay, yeah.
So, did the predictions think that by 2050 we'll have the cheaper batteries?
So there are various technologies. Um, just lithium-ion battery is not the only solution. Okay. Yeah. All you need to be able to, let's say, if you have 1,000 Hoover dams running, you need those 1,000 Hoover dams to be charging batteries, so you can have energy for the night times and stuff like that. That's the claim. Okay. And so I'm trying to give you the magnitude of the problem. Okay. So, and again, so here's how you remember this kind of stuff. So how much, so what do you need to run the world? About 15,000 gigawatts, okay? And 1,000 of 1,500 gigawatts would be 10%. So whatever your power plants are, you need roughly 10% in batteries, okay? So that's how you think about it. All right, so again, you've seen this, okay, by 2050, with existing technologies. Now we know that there's going to be all kinds of solutions. Nuclear energy is good, and so on. So we'll have nuclear energy will play a part too. But according to these guys, 40% will come from wind and 60% from solar energy. You can run the planet on that. Okay. All right. All right. So how are we producing electricity currently? So this is how we're producing electricity currently. Okay. So these are magnets. Why isn't this showing up on my? What happened? Oh, there you go. All right, so the way this thing works, I mean, you've seen this plenty of times. Here, these guys are magnets. You turn this wire between the magnets, and you're producing the energy you put in is being converted to electricity. Okay? So it's a matter of figuring out how to turn that wire. And we will learn one of the solar technologies is you can take a dish, concentrate solar light. So one of the ways you can do it is like this. Take a dish, concentrate sunlight on some device, heat it, use that heat to produce steam, and the steam will turn that. Okay? This is a plant in Arizona. Okay? And I'll show you other plants. So here's another way to do it. Okay? So these are all mirrors. They're heating water or salt these days in there. You're heating the salt, storing heat, and what do you do with the heat? You boil water, produce steam. Why are you doing that? Turn the wire, okay, to produce electricity. So you can produce electricity like that. Okay. So this way of harnessing solar energy, we got about 10 Hoover dams worth in the world. Okay. Has anybody seen anything like this? Where have you seen it?
In Nevada, when we like driving past.
Okay.
These big like.
Mm-hmm. Yeah. So there's 10 Hoover dams worth of it. Okay. Now, if the world were completely renewable, how much batteries do you need? I'm sorry? 1,000 gigawatts. Very good. Okay, so in Spain, in 2011, 12 years ago, using a device like this is called a solar power tower. Okay. Torresol's 20 megawatt concentrating solar power plant became the first ever to generate uninterrupted electricity for 24 hours straight. Okay. So this can act like a battery. With molten salt heat storage systems, the need for batteries is eliminated, making them viable solutions in many situations. Okay. Did you guys understand that? Okay. So this concentrating solar is more expensive than solar panels. Okay. But that's fine. As long as these are cheaper than lithium-ion batteries, you'd build these. Okay. How many of these do you build? About 5%. Okay. The thing is, of course, you probably can't build it in Canada. I mean, I don't know if it would make sense to build it in Canada. It would, if it would be economically viable. But anyway, this is a solution. Did you guys understand that? Go ahead.
Me?
Mm-hmm. Something is you were thinking,
Oh,
and I could hear it.
so how is the energy stored in this molten salt storage?
Okay, so you heat something, and as long as it doesn't cool down, you just make sure it doesn't cool down, then it's storing heat.
Okay.
How long can you store it? Well, you can store it up to a week, apparently. Okay, yep.
Now, is that salt the kind of salt that we ingest?
No, so here's the salt. Okay, so here's the deal. Okay, so you want to store the heat as much as possible. Okay, and what is it about a bank that you like? What does a bank do? You can put your money there. How much money can you bring out from the bank?
Whatever you put in.
No, yeah, all of it. Okay? Okay, so that's what you like about a storage device. Okay? Same thing with salt storage. Okay? Whatever heat you put in, you want to be able to get it all out. Okay? Well, you'll lose some to cooling and all that kind of stuff. Okay? So anyway, here's the deal. If the salt remains liquid at low temperature, the lower the temperature it's remaining liquid at, the more heat you can extract. Okay? Calcium nitrate can reduce the melting point to 131 degrees Celsius, permitting more energy to be extracted before the salt freezes. Did you guys understand that? Okay. In addition, now there are several technical calcium nitrate grades stable at more than 500 degrees Celsius, allowing more heat to be stored. Okay? So what you're looking for is some kind of salt mixture where it stays liquid at low temperatures and it's still liquid at high temperatures. So the larger the range, the more energy you can store and the more energy you can extract. Okay? So the first commercial molten salt mixture was common form of saltpeter, sodium nitrate, and potassium nitrate. Okay? So those were the salts. All right, I went all over, but hopefully you understood some of this stuff. Yeah. So even this kind of devices are more expensive than photovoltaics. They serve the purpose of, they can act like batteries. You can store heat in the salt there. Okay? And the tanks are insulated and can store heat for a week. Okay? So you could always heat the salt during the day, and when at night the sun is not shining, you can use the heat stored to produce electricity. Okay? And what?
Tanks, those little silver things down at the bottom?
I'm sorry?
Are the tanks those little silver things down at the
What are these?
I thought
Those,
those were mirrors.
yeah, those are mirrors. Those are
Where's
mirrors.
the tanks? with Salt stuff in it.
There.
That?
Yep. That's a tank.
That's really small.
Well, this thing is as tall as a football field.
Gotcha.
Okay. So that's so tanks that power 100 megawatt. What is 100 megawatt? How big is it compared to Hoover Dam? 1,000 megawatts is 1 gigawatt. So this is a tenth of a Hoover Dam. I'm sorry?
It's 100 million.
Yep. Yep. So this is a tenth of a Hoover Dam. It probably costs nothing. Okay. So the future looks good for you guys. Okay. All right. So again, so this, like I said, this is in Arizona, and you can concentrate sunlight. This is a Stirling's engine, which you can use to turn that piece of wire to produce electricity. Okay. Okay. So we do electricity from the sun can be generated one of two ways, using solar radiation to run a heat engine to drive a generator. Okay. So this is a heat engine, and you can use that to drive a generator. Use a so this stuff is turning that piece of wire between a magnet. Okay. And that's how we've been producing electricity for over 100 years. Okay. Now this technology is newer, the photoelectric device or photovoltaic cells, and we'll talk about that. Okay. So that's the second half of the chapter. And that story is a little involved. So we'll get to that. Okay. So global concentrated solar power capacity. This is slightly old information, but it's about 6.5 gigawatts, but about 10 gigawatts. Okay. So solar energy is focused to a heat engine, which drives a generator to produce electricity. Okay. And the next chapter we'll talk about windmills and so on. Okay, so here's the photovoltaic capacity. This is solar cells. Okay. In the world today, about, again, this is 2025, we're roughly there. 900 Hoover dams worth of photovoltaics have been installed in the world. Okay. That's about a little less than 10%. Okay. And they're installing about 70 gigawatts per year in the world. They're building 70 Hoover dams worth of stuff per year. Okay. Can you build 70 Hoover dams in a year? No, you can't. So with solar cells, it's cheap. You just throw them out. If you drive by on I-10 and 995 and stuff like that, now you go into Georgia, you'll see a lot of solar plants popping up. Okay? So what is driving this? Of course, price. Okay. Back in the late 70s and early 80s, each watt cost about $100. Okay. So this was the cost per watt for a solar panel. A solar panel to produce 1 watt of electricity cost you $100. Okay. And so only NASA could use it for satellites and stuff like that. They were willing to pay that kind of money. You know. Now, to put it on your roof, the deal was the price had to come below 50 cents a watt, and now it's already there. Okay. So if FPL is going to invest in a new power plant, it's not going to build a coal power plant. It's building solar plants. Okay. Right, Mr. Swanson came up with this law, and this is basic economics. Okay, so this is module price, and you see this is a log scale, log scale. What the statement is, okay, so what this graph is, what Mr. Swanson predicted, which is simple economics, states that as prices of photovoltaics fall exponentially, the total installed photovoltaic in the world panels grows exponentially. And that's what this is showing you. So again, we'll talk about the first method of the using solar energy to run heat engines. Okay. By the way, okay, in 2022, global installed electricity generation capacity from photovoltaics was about 700 gigawatts. This is about 100 times that from concentrated solar power. Okay, so what that statement is saying is, so this is concentrated solar power. You're using solar energy to run a heat engine. And photovoltaics are, where are the photovoltaics? You guys have seen solar panels, and I don't even have a picture for solar panels. Isn't that sweet? Okay, here. So here are solar panels. Energy from this kind of stuff, the installation is 100 times greater than the concentrated solar power, than the salt. Why? That was the statement. Because this was cheaper. Okay? But eventually, you will have more of those concentrated solar powers because they can act like batteries, once we get the technology straight. Well, I'm sure the technology is good. You guys understanding this stuff?
Do you think eventually they'll mandate like solar panels and stuff, or?
You don't have to mandate. What do you buy? The cheapest and the best stuff. Mm-hmm. The marketplaces drive it. And I mean, inherently, we do think about what's best for our children. Okay? Maybe we're not willing to spend a whole bunch of money on it, but you guys understanding this stuff? Mm-hmm. All right, so here's another configuration. So here's one configuration. You're concentrating solar panels. These are parabolic dishes. You drive a heat engine, which can turn the wire. You can, here are parabolic troughs, and a fluid flows through there, through a pipe there. That's where sunlight is concentrated. You heat the fluid, produce steam, which turns that wire. Okay? And of course, the thing with these things is the mirrors have to turn as the sun goes across the sky, and so on. Okay, this heat engine can operate at 26% efficiency. Okay, so I will briefly go over the power towers again. Again, these are all flat mirrors. I guess these mirrors seem to be covered. So there is the mirror. And right now, so these mirrors are aligned to that. Okay, right now this is not operating, but anyway. So all these mirrors would be pointing sunlight there to that tank, which will, and you're heating a salt. Okay, so early designs heated water and use the resulting steam to power a turbine. Newer designs use molten salts to store the collected solar heat. which can be used to operate a generator. Okay? So you can store more heat in the salt, and it can store it for a longer time. Okay? Again, what you're looking for is for the salt to be liquid in a larger temperature range. Okay? If it's liquid at lower temperatures, you can extract more heat out of the salt. And if it's liquid at a higher temperature, you can store more heat. Okay, so the larger the gap, the better it is for you guys, for us. Okay, so tanks that power a 100 megawatt turbine. So a tank containing salt that could be as big as, so this is a tenth of a Hoover Dam. For 4 hours would be about 9 meter tall and 24 meters in diameter. So 24 meters, so about twice the size of this room. Very small. Okay, so this much salt, and you could 100 megawatts is you could run 100,000 homes. Okay, for 4 hours. All right, so again, remember this number. So this is a good number to have in mind. In 50 years, you need 1,000 Hoover Dams worth of batteries, okay, when you're running the planet on renewable energy. Okay. So these are the, okay, so onshore wind is the cheapest, offshore, then photovoltaics is the next cheapest, then offshore wind, and so on, and concentrating solar power. All right, now we will talk about how photovoltaics work, okay? How solar panels work. So again, this is a slightly involved story, okay? And please stop me if you have questions. Before we go into this, do you have any questions on the concentrated solar power? All right. Here's the model of an atom. Here's the nucleus. These are the various energy levels for the electron. Okay. So if this was a hydrogen atom, it only has one electron, and the electron will be in the lowest level. Okay. And these levels are, so here's another way of drawing. So this is how it's rough. It's physical model. And here's the energy level. So this is the lowest energy level. That's the next higher energy level. Next higher energy level, and so on. So what is it? What is our goal? Our goal is to capture sunlight. Okay. So our goal is to capture light coming in, okay, and turning it into electricity. Okay. So here's a simple process. Here's a photon that comes, the atom absorbs it, and the electron get excited. Okay. Now, if the photon has enough energy, the electron can get kicked out, and then that electron can run through your washing machine and come back, do its job. That's our goal. Okay. Now, here's the deal. So right now, I'm just talking about an atom, and we'll elaborate this story. The electron gets excited, and what happens is, normally within a billionth of a second, it'll go back to the ground state and emit that photon back. Okay. So let me show this process. So a photon came in, a unit of light came in, it excited an electron, and when that excited electron falls back to the ground state, the lower energy state, that photon is emitted. Okay. And that happens generally within a billionth of a second. Okay. So keep that in mind, and we'll talk about that. Okay. So here's the levels. Here's a very simplistic diagram. Okay. And this formula just gives you the energy of these levels. Okay. So the lowest one is n equal to 1. These are quantum numbers. N equal to 2 state, n equal to 3 states, and so on. You have up to n equal to infinity states. Okay. You might have seen this in your chemistry classes. Okay. Now, if you have a multi-electron atom, hydrogen is the only one with one electron. All the rest have multiple electrons. Okay. What happens is this n equal to 2 level has several sublevels, and those sublevels get split. Okay, that's what it's saying. Anyway, it doesn't matter. These are the energy levels. Okay. Each level can only hold 2 electrons, one with a spin up and one with a spin down. Okay. So in chemistry, so the sublevels are named as S, P, D, F, and so on. Those correspond to angular momentum quantum numbers. Eventually, if you see them, so the 4 quantum numbers that an electron can have is N, the principal quantum number, L, the angular quantum number, M, the Z component of the angular momentum, and the spin quantum number. Okay. So this is sort of like the social security number for an electron in an atom. Can 2 people have the same social security number? No. So that's the rule. Okay. Every electron has to have a unique set of quantum numbers. Okay. All right. So you can 2 electrons can have the same one, and they'll just have a spin up and down. Okay. Anyway, so these are the energy levels. Okay, so here's silicon. Silicon is has an atomic number of 14, so it has 14 electrons. Okay, and here's the electronic configuration of silicon. Okay, in the 1s level, it has 2 electrons, spin up, spin down. In the 2s electrons, 2s orbital has 2 electrons. 2p, it has 6 and 4, 10, and here are the 14. Okay, so this is the electronic configuration. So here's a diagram. Here is the electronic configuration that chemists. This is how chemists write 1s 2. In the 1s orbital, it has 2 electrons. 2s orbital, it has 2 electrons. 2p orbital, it has 6 electrons. The 2 is missing there. 3s 2, 3p 2. Okay. Go ahead.
What does the S and like the P stand for? Do they stand for anything, or is
So
it just
So for this is the principal quantum number. This can take 1, 2, 3, and so on. Okay. So let's say if n equal to 3, what does n equal to 3 mean? We're talking about 1, 2, 3. We're talking about this orbital. Okay. And this orbital has sublevels. It's not drawn here. You can think of it as sublevels. Okay. So the sublevels. So the next quantum number, which tells you about the sublevels, hello there, pour it out on a piece of paper or something like that. Don't worry about it. All right. The sublevels, the thing is making noise. No worries, no worries. Yeah, no, I don't care when people bring food in. I just don't want it being noisy. That's yeah, no worries, no worries. And I got mad because you're not even sharing it. I wanted some. All right, so the sublevels are, it can take values 0, 1, and 2, up to n minus 1. So if you had n equal to 5, L could take values. What values can L take? 0 to 4. Okay? And so this is called S, this is called P, D, F, that's all.
okay?
All right. That's what the chemists like to use. What? Yep.
So in that notation, S1, 2 would be N, the
N-
N1
Mm-hmm. L is 0.
Okay.
Yeah, that's what that would mean. So 2p would be,
2P,
what is 2p would be? What would this be? This is n is 2, and L is 1. Okay. 3d, n is 3, this L is 2. Okay. So that's the notation. All right, we're good? All right, we're building a story. Okay, so ask questions now. What are we trying to understand? Well, our ultimate goal is how photovoltaics work, how solar panels work. Okay, that's what we're building towards. And they are built using silicon semiconductors. Okay, so right now a lot of the solar panels are built using. So, okay. So here is the electronic configuration of silicon. All right, now of course, so what we're going to do is we are going to build semiconductors. Now what happens is if you take a whole bunch of silicon atoms and build a solid out of it, each of these levels smears out. So if you have 1 billion atoms, each of these will smear out and become 1 billion energy levels. And that becomes a band. Okay? Energy band. Okay? So if an atom is by itself, all you have is these levels. But now if you make a solid out of it, okay, each of the levels will turn into a band. Okay, so in a sample of solid silicon, the interaction between atoms causes the energy levels to smear out into bands, and it also causes the p bands to split into 3 sublevels. Okay, so these energy levels become bands, and those are the bands. Okay. And again, so the bands are just a collection of energy levels, and there are electrons in this energy levels. Okay? You guys understanding this? Okay. All right, what is your goal? Here's energy coming from the sun. An electron captures it and goes over there. Okay? And you capture this energy packet from the sun. Now, what happens generally is that electron will fall down back within a billionth of a second. Okay? Emitting the photon again. Okay. All right, so here is a photon got captured, the electron got excited, except that within a billionth of a second it wants to fall back. And you want to prevent that. And how do you prevent that? That's the Nobel Prize winning idea. Mm-hmm.
can they go multiple levels or just?
Yeah, it just, so they jumped depending on what energy you gave. Okay? You hit it with a hammer hard enough, it'll jump over there. Okay?
Can
Yeah.
a photon that was released cause another interaction different?
Yeah, it can. Okay. So the energy of the photon, okay. So in silicon panels, half the energy is not utilized because it's not enough energy to cross this band gap. So it's pretty good, even if you have a panel that's 15% efficient, half of it you can't even absorb. Off the half, we got you almost captured a third of the light. Yeah. Yeah. You guys following this? Go ahead.
So he asked if it jumps it can jump multiple bands, would it also fall multiple bands too?
Yes, so if you gave me $10, I jumped there. If you gave me $100, I jumped there.
But then it's just gonna fall back.
Yeah, and I can spend $20, $30, and so on. Okay? So here's the diagram. If this photon has exactly the energy difference between these two levels, it can jump there. You have to have the exact same energy. Okay? You either absorb a photon or fully or not. You can't absorb half a photon. There's no change here. Okay? So this energy has to match exactly the energy difference between you. Okay? But the thing here is, the advantage here is this is a band, there's billions of levels here, there's a band billions of levels. So you could, as long as you have energy greater than this, you can absorb a photon to go from here to there. Okay? Now the problem you want to listen carefully about is this guy will jump back within a billionth of a second, and you're trying to prevent that from happening. Okay? And use this electron to run your washing machine or whatever. Okay? All right, so let's talk about that. Yep.
This is probably a really dumb question, but what's
Mhm.
a photon?
Oh, a photon is a packet of light.
Okay, I
Mm.
thought it was like, okay.
Okay. So the light that you see comes in packets like this, and the energy of a photon is h Planck's constant times the frequency of the light. Okay. And the frequency is also denoted by nu. Some people write it like so, h equal to h nu. Okay. So that's the energy of the photon. Yep.
Since the photon needs to be exactly the right energy to push it up one level,
Yeah, if the energy difference between two levels is 7 electron volts, the photon has to have that exact same energy.
do they have to use a medium to reduce the energy of the photon, or is there such a wide variety of photons that doesn't need to?
Yeah, the sunlight has a wide variety of photon. Yep.
And did you say we know how to keep it from going back, or we haven't figured that out?
We know how to do it. That's a Nobel Prize winning idea. That's a very, and we'll talk about that. Beautiful idea. Yep. All right, so here are the basics of this idea. This is an electric field. Okay? In an electric field, a positive charge will move in that direction and a negative charge will move in the opposite direction. Okay? So okay, so before I go there, okay. So when the photon got absorbed, this electron jumped over there. This is called the conduction band. The electron is negative, and this hole that was left behind acts like a positive charge. Okay? You guys understand that? Okay. So, and this makes sense. The electron, the negative charge, is being attracted by the positive charge, and that's why it collapses there. It recombines within a billionth of a second. And you're trying to prevent that from happening. How do you prevent that from happening? Okay, so here's an electric field. An electric field, denoted by E, applies a force on a positive charge like that, and on a negative charge, the force is like this. So they move in opposite direction. Okay? So wherever you absorb, so the idea is like so. The idea is this. You absorbed a photon, and what did you do? You created a hole and an electron there. So how do you prevent them from recombining? If you could create an electric field at the point of creation, they would move in opposite direction. They wouldn't have a chance to recombine. And that's the idea. Okay? And that's what happens in a photovoltaic cell.
Can you repeat that?
Okay.
Sorry.
Yeah, I'll do that in a second. Yep, go ahead.
So they're creating that field like within that span of time?
No. Well, it's a permanent field, and how do they create it? And I'll tell you that. And so that's what the billion-dollar industries where chips and all those things are made. Okay. All right. Okay. So what is our goal? Our goal is to absorb this photon, right? The photon absorbs and created this hole and electron, right? You understood that part?
Yes.
And that's what this diagram is telling you. The photon came, got absorbed, this electron got excited there. This electron is negatively charged, this hole is positively charged. Okay? Now, if you didn't do anything about it, this guy recombines within a billionth of a second. Why did they recombine? Because this is negatively charged, this guy is positively charged, and they attract each other and they recombine. Okay? You're trying to prevent this. Okay? And the idea was if you had an electric field, the electric field has a force on positive charges in this direction, in the direction of the electric field. On a negative charge, it's in the opposite direction. So wherever you created this electron hole pair, by absorbing this, if you had an electric field at that location, huh? The positive charge would go in this direction, this would go in that direction, and they'd get separated. Okay, that's that.
Sorry,
Mm-hmm.
why do we not want them to, recombine? Why do we not want it to fall back in?
It's like your boss paid you your salary and you gave your boss the money back. You want to spend it outside. When you're okay, so here's a electric car or whatever. Here's some device. So your toaster. An electron has to travel through the toaster to make it work. An electron and that's an electric current has to travel through it. Okay, so you want that electron to go through the toaster and not just recombine. That's when it does work.
Okay.
All right. Okay. Mm-hmm.
When you activate or when the field's active, does
Mhm.
the photon still be emitted after everything is done, or does the photon stay there?
Oh, the electron loses the energy when it goes through your toaster. It cooked your toaster, didn't it?
Yeah.
So that's where the energy got used. Okay, so have your antennas up. What we're trying to do is prevent the electron hole to recombine. And we're going to learn that over several slides and several minutes. Okay? All right, so we understood that these levels of the atom become bands when in a sample of solid silicon, the interaction between the atoms causes the energy level to smear out into bands, okay? So here are all the 1s electrons from all the silicon atoms living there. Here are all the 2s electrons living, okay? So if you had a billion silicon atoms, this had billion levels in them, okay? That's what that means. Here are all the 6 2p electrons living. These are all the 3s electrons living, and this is the 3p, 2 electrons from each atom. They've filled that band. So this is known as the valence band. This is the conduction band. Right now, this conduction band is empty. It has no electrons. So a pure silicon crystal cannot conduct electricity, okay? So this cannot run your toaster. Okay. So to run your toaster, you need a bunch of electrons here. Okay. Well, how do you get a bunch of electrons there? Well, you absorb a bunch of sunlight and put a bunch of electrons there. Except that these darn electrons want to fall back there. Okay, and you got to prevent them. All right. So here's what we do. Okay, and again, this is just showing you how electrons go from here to there by absorbing photons, and when they fall back, okay. So if a photon with sufficient energy interacts with the atoms of a piece of silicon, then one of the electrons in the first 3p band can be excited to the second 3p band from here to there. Okay, the missing electron is referred to as a hole. So this essentially the gap left behind acts like a positive charge. Okay. In semiconductors, the highest occupied band is generally full and is called a valence band. This is called a valence band. The next band, which is empty initially, is called the conduction band. This is the conduction band. So you're trying to excite electrons from the valence band to the conduction band. Okay, so in principle, here's a silicon crystal. You can shine light and you can create an electron hole pair. This is just sort of a cartoon diagram. The electron hole pair in pure silicon crystal would recombine within a billionth of a second, okay, and not do anything for you. The design of a functional photovoltaic cell requires figuring out how to eliminate recombination, okay, and have the electrons flow through an external circuit. Okay. A p-n junction. So this is what you want to remember, and that's you've had LED bulbs. That's what they use. Okay. So an LED bulb and a photovoltaic cell are exactly the same. Okay. In a photovoltaic cell, you're using photons to produce electricity. In an LED bulb, you're using electricity to produce photons. So they're doing inverse things. Okay? All right. All right. So doped semiconductors. Okay, so pure semiconductors, pure silicon doesn't do the job. What you have to do is you have to dope it. Okay? You have to put impurities in it. And the impurity levels are 1 in a million, meaning for every million silicon atoms, you put 1 impurity atom. Okay? So those are the numbers. For N-type impurities, okay, so silicon, which is atomic number of 14. So coming back to this, okay. So these are the valence electrons, okay. So silicon has 4 valence electrons, okay. So the kind of doping you do is for N-type, the valence electrons is 5, and for P-type, the impurity has 3 valence electrons. Okay, so that's what you want to remember. Okay. All right, so for an N-type impurity, how many impurity atoms are you putting? 1 in a billion, 1 in a million. The impurity atoms have 5 valence electrons, that's what, okay? And these impurity atoms have 3 valence electrons, okay? So N-type impurities have 1 more valence electron than the host. The impurities give an electron conduction and become positive. Okay, we'll come to that in a second. Okay, what are those? What is an N-type? Phosphorus is used to produce N-type and boron for P-type semiconductors. Okay, so those are the impurities. All right, so phosphorus atoms, so they have this energy level there. Okay, now this is crucial. So this is the conduction band that was empty. This energy gap is so small that even room temperature will excite these guys. Okay, so all these electrons go from there to there. What happens to the phosphorus atoms? They have become positive ions. Okay, so these are all donors. You want to understand this because this is the $1 million answer. All those electrons have gone there. And they've all become positive ions. And they're called donor guys. Okay. What happens there? So these are the boron atoms. their levels are close to the valence band, so at room temperature, all the electrons get excited there. Okay? They fill these guys, they become negatively charged, the acceptors are negatively charged, and you've left a bunch of holes there. Holes are positively charged. Okay? You guys understanding this? Okay. Questions? Because now's the punchline. The punchline is coming at you. All right. So here was the silicon crystal. We have doped it in the P region. You doped it with boron. Okay. And the borons are acceptors. They become negatively charged. Okay. The borons are these atoms. They have accepted electrons and they become negatively charged and they've left behind holes. Okay. So the borons, these guys are negatively charged. I'll draw them negatively charged. These guys are donors. They've donated electrons. It's called N-types because the charge carriers are negative charge carriers, which are electrons. These are called P-type, positive charge carriers. Holes are the charge carriers. Okay. Don't worry about the D. So these guys have donated. Okay. And this is called so this is a P region, this is an N region, and that's why it's called a PN junction. You created a PN junction here. Okay, these guys are negatively charged, and so they have repelled all the electrons of the carriers here, and they've repelled all the electrons there. These guys are positively charged, holes are the carriers here, they've repelled all the holes there. Okay, and so here's a region where there are no free electrons or holes. So this is called a depletion region. But here's the deal. These guys are positively charged, here's the negatively charged. And this creates an electric field pointing in this direction. So at the PN junction, you have a region where there's an permanent electric field created. And now,
Did you just say electric permanent?
a permanent electric field.
Permanent.
Yeah.
Permanent.
And now you've solved your problem. How did we solve our problem? Okay, now we're going to shine sunlight here. And in this region, you create an electron-hole pair. And this electric field is just sitting there and separating the electron and the hole, preventing it from recombining. And this electron now can go to your toaster and make you breakfast. And that's how a photovoltaic cell works. I guess.
N-type impurities have one electron?
I'm sorry?
You said N-type impurities have one electron?
One electron extra. They have 5 valence electron. Yeah. Mhm. Okay. And the crucial part is so you got to choose the right impurities whose level is sitting right below this conduction band. So these electrons can be thermally excited. Yeah. It's very cool if you guys understand it. Yeah.
And is silicone always used?
Hmm?
Yeah.
Well, yeah, most of them are silicon, but there are other materials that are being used. So all the ones that you see on the roofs here. Okay. Nowadays they have organic semiconductors and stuff like that. But you guys understand that? So I'm going to let you guys ask questions, or I'm not going to muddy the water anymore, and I'll let you read this slides. Okay. Okay, so here the physical width of the depletion region is in typical silicon diodes range from a fraction of a micrometer. 1 micrometer is about 10,000 atoms. Okay? To tens of micrometers, depending on the device geometry doping file. So this is where you absorb most of the photons. Okay? So here's the probability. If you absorb the photon in the depletion region, unit collection probability for carriers generated in the p-n junction. So if you generate a whole electron hole pair, there's zero probability that they'll recombine. That's what that thing is saying. Okay? So this is off the depletion region, they all recombine. Okay? So here you're this far away from the depletion region, and that the electron hole pair recombine. That's what that graph is telling you. Okay? Okay, so you did a magical thing. Okay? Doping concentrations can range from 1 in a billion to 1 in 100,000. Okay? Phosphorus is used to produce N-type and boron for P-type. Okay, so one more thing I'll point out. So the electrons go through to the N region, and there's a bunch of electrons, and these electrons are driven like that. Okay? The holes go to the P-type region. Okay? So here's how this looks. Here's the p-n junction. That's where the sunlight is absorbed with probability 1. There's the n-type at the top, p-type at the bottom. So the electrons flow like that, and then go to the bottom like that. Okay? So that's where the sunlight is being absorbed. Okay? Okay, a typical single cell 10 centimeters, so a wafer that big, 10 centimeter in diameter, produces 1 watt of electricity. Okay, and that's around noon time. Okay. Typical cell efficiencies are about 15%. About 55% of the solar spectrum includes wavelengths too long to liberate photoelectrons. What that means is about 55% of the sunlight cannot excite electrons from there to there and cannot be absorbed. All right. So here are expensive solar panels. This solar panel has material to absorb this light, this layer. It has various layers, triple junction devices. Efficiencies can be improved from white light by combining devices with spectral response that better cover the range of incident wavelength. So you can have one junction absorbing this, another junction absorbing that light, and another junction absorbing that light. Okay, so you saw that you cover these black spots with photovoltaic panels, and you can run the planet. Okay, and you can rule the world if you want it. So here's photovoltaics connected in series. So the voltage across the p-n junction, so that permanent electric field, creates about half a volt. Okay, so if you connect 3 panels in series like this, you get 1.5 volts. If you connect them in parallel, okay, so the current is the same, the voltage increases. If you connect them in parallel, the current increases and the voltage is the same. Okay. Standard commercial modules that you see, so on the rooftop that you see those modules, they have a power output of roughly 100 watts, one panel. Okay. So one of these guys has 100 watt power output. Yeah. So here is an LED. Again, it's a p-n junction. Here are the holes. Here are the electrons. Okay. So remember, the electric field was pointing in this direction. Okay, and the electrons want to. So there's the there's the electric field, and the electron wants to travel in this direction. So there's a bunch of electrons. So if you connect a battery like that, this will force the electrons to go in that direction. So the electrons are climbing a hill, but once the electrons cross the hill is the junction. Once the electron cross over there, they can combine with the hole. The electrons can combine with the hole and emit light, and that's the LED. Okay? And LEDs are 90% efficient. Yeah. You guys remember the old bulbs? Those were about 5% efficient. What does that mean, 5% efficient? 95% of the electricity is converted to heat, not to light. That's the job of the bulb. Only 5% of the electricity is converted to light. In an LED bulb, 90% of the electricity is converted to light. Yeah. So in the planet, on Earth, if you turn every light bulb, replace every light bulb with an LED bulb, you can shut down 3,000, roughly 3,000, 2 to 3,000 coal power plants. Okay. Right now they're expensive, and so we're not doing that, but all cities have done that because